Hello students, now today we are here with our next topic, that is moving coil galvanometer. This is our last topic for this chapter. Okay, so we'll be starting with moving coil galvanometer. What does that mean? There is a coil which will be moving and which makes a machine that is known as galvanometer. Okay, so first of all, for what it is used? It is used to detect or measure small amount of current. It can detect or measure only small amount of current of the times of microns, like 10 raised to minus 6 ampere, okay, microampere, okay, or milliampere, you can say milliampere. Okay, so here I have written the use. It is used to detect and measure only small current. Okay, I have underlined over here that it can detect only very small current. Okay, now we'll move towards the principle. What is the principle? Principle is the torque acting on the current loop. Okay, in the previous lecture only we had discussed about the torque acting on a current loop. Okay, the same principle will be applying over here, torque on a current loop, and we have already studied about the formula, that is tau is equals to NAIB. Okay, where N is number of turns, I is current, A is area vector, and B is the magnetic field. Okay, so how the principle works? If more current is passing, then the torque will be more, because torque directly depends on current. Okay, so if current is increasing, torque will also increase, which means that if current increases, torque will increase. If torque will increase, then there will be deflection, because a pin is or a pointer is attached to the coil. Okay, so if the torque increases, the pointer deflection will increase. Okay, which means more the torque, more the deflection, and more the deflection, more will be the reading. Okay, so after this we'll move towards the construction. Okay, here you can see the figure of moving coil galvanometer. Okay, so first of all, in the basic setup, there are two horseshoe magnets, horseshoe or you can say concave shaped magnets. This is north pole and south pole. They are permanent magnets and made up in the concave shape. Okay, this shape you can see concave shape, or you can also say horseshoe magnet. Okay, why specifically this shape? To obtain the radial magnetic field. To obtain radial magnetic field. Remember, here we had NAIB sin theta if it was in magnetic terms, but here to make that sin theta equals to 1, we are using the radial magnetic field. Okay, so here we have a radial magnetic field due to this. Okay, in between we put a soft iron core. In between there is a soft iron core. It is of cylindrical type, like this. Okay, this is the top view of the moving coil galvanometer. Okay, here in the center there will be a soft iron core of cylindrical shape, on which there will be a loop will be wounded. Okay, in this manner. Okay, loop will be wounded in this manner. Okay, so here in the top view of this cylinder you can just see a circle, and this circle is this. Okay, on top of that, this red lines you can see, that is the winding of the wire. Okay, then there is in the center there is a spring attached. What happens with the spring? Spring keeps the restoring force. Okay, spring को क्या करता है? Spring को कभी भी घुमाते हैं. What it will try? It will always try to come in its original position. Okay, spring को खींचा तो भी original position में आने की try करे. If you twist the spring, then also it will try to come in its original position. Okay, that's why spring is attached in the center. The spherical shape or the this spherical shape, you can see that is a spring. Okay, now attached with this soft iron core is the pointer. Okay, as the rotation, as the torque acts on this wire or the coil, winding coil, what happens? That there will be due to this winding coil, there will be torque in this iron core, and due to this rotation it will rotate the pointer, and when it will rotate the pointer, we can see the deflection over here, and this is your scale. Okay, this will be your scale. So that's it about the main construction part. Okay, I hope you have understood it. Just to show you this part, what I'll use this. Suppose this is a iron core, soft iron core. So what will happen on this? The ropes will wires will be attached in this condition. It will be wounded in this condition. Okay, so in the top view you can see just the circle that is drawn over here, and there will be wires. Okay, now one thing also you can see that if you look at from front, and a cross section, then the triangle will be in the form of this only. It will be in the rectangular form. Okay, the coils will be in this form. Okay, I hope the construction is very clear to you. You all can draw this construction. Okay, this part is also not required. This was just to make you understand. Okay, now we'll move towards the working. Okay, we'll move towards the working of it. Here I have written working. I have written it in very short. Just don't try to copy from this. Try to copy and understand it. and you can write much more things from your own. Listen to my words and then you can make your own working. Okay. Now as the terminals are connected, whenever the current starts flowing from the coil, when the current starts flowing from the coil, what will happen? It will produce the torque. Okay. As soon as it produces the torque, what happens? This iron core will start to turn itself. Okay. It will try to rotate itself. As in when the current goes inside, there will be torque produced and torque tries to rotate itself. Okay. So whenever a torque tries to rotate itself, what will be there? We have a spring which produces a restoring force on it. Okay. For example, I will show you how the restoring force acts. Suppose I have something over here. Okay. This is in stable condition. As and when I apply torque on this, okay, what happens? It tries to come in its original position. As and when, once again, if I try to rotate it, it tries to come in its original position. What does this mean? That whenever I am applying external torque, there is some torque inside it which tries to restore itself. Okay. Some internal torque is produced which tries to cancel out the applied torque. Okay. So here I have shown that suppose there is something hang over here, and if there is a weight, if we try to rotate it, what happens? It will try to get itself in original position. Okay. Due to its material properties. Okay. So for that we know that there is a torsional constant. We say it's C. Okay. So what is the restoring force? This C is the restoring torque per unit deflection. When there will be 1 degree of deflection, 1 degree of twist, then C will be the torque, or you can say C will be the torque produced. That is per unit degree deflection, per unit degree of twist. Okay, here I have written restoring torque per unit degree twist. So if it is 1 degree, then the torque will be equal to C. If there is 2 degree, then the torque will be equal to twice C. If there is 3 degree, the torque will be equal to thrice C or 3C. So if the angle is moved by phi, okay, if the angle is moved by say phi, okay, the rotation due to torque is say phi, then the restoring force will be equal to tau equals to phi into C, where C is the torsional constant, or you can say C is restoring torque per unit degree of twist. Okay, I hope you have understood up till this much. So now, what is the amount of restoring force? It is equal to the torque produced. Okay, suppose once again I will take what will be the torque produced in this. Suppose I twist it in this direction. What will the amount of torque or restoring force? It will be equal to the amount of torque that is applied. Okay, so here I can write that torque on coil is equals to torque of restoring force. Okay, what is the torque on coil? We already know torque of coil is equals to NIAB, that is number of turns into I into A into magnetic field. Okay, so I have written NAIB is equals to phi C if there is phi degree of twist. If it is phi degree of twist, from here we can say, so I can compare these two things. Okay, okay, suppose if it is not visible to okay, I hope everything is visible now. Okay, so here NAIB is equals to phi into C. So I can rearrange this equation. I am just rearranging this equation. What can I write? Because I want it in terms of current, because I want to measure the current. That's why I have made current the subject. So I can write it in the form of I equals to 5C upon NAB. Okay. Now here you can see C is constant. C is torsional constant, so it will remain constant for any material. N is number of turns, that will remain constant because we have kept the number of turns that is fixed once you have made the material. Okay, or you have made the galvanometer. A is the area will also be fixed, and B is the magnetic field. That magnetic field of this magnet will also be equal, will always remain the same. Okay, so from here we can write I is proportional to phi. Can I write I is equals to I is proportional to phi? What does that mean? The amount, more the twist or more the restoring force or more the twist produced, is showing the more the current is flowing. The more the current is flowing, the more there will be the twist. Okay, vice versa. If current is more amount of current is moving, okay, the value of phi will keep on increasing. Okay, so it will detect or it can measure the current. If more current is passing, it will show more deflection, which will be seen over here on the scale. Okay, I hope this much is very clear to you. So this was all about the moving coil galvanometer. Okay, now if you want to increase okay, one more important topic, current sensitivity. Okay, what is current sensitivity? Current sensitivity in simple sense, like let us talk about sensitivity. what does sensitivity means? It depends on person to person. Like if I say you something, there may be a students which will take them on heart or take on mind. Okay, some they will just let it go. They will not be affected at all. So each and everything has some sensitivities. Like if you give something, some small amount of input, what will be the output? Okay, if I give some amount of input, what will be the output? That shows the sensitivity. For small input, if there is large output, that shows that sensitivity is very high. For small input, if I say I get only small output, or for large input also I get small output, then we can say that sensitivity is very small. Okay, so that is current sensitivity, means the sensitivity of this moving coil galvanometer. Okay, so to define this, it is defined as phi by I. Phi by I. Phi is the input, I is the input, and phi is the output. For small current or big current, how much phi will you get? Okay, if you are changing the amount of current, what will be the change in twist? Okay, so phi by I is defined as your current sensitivity. So from here I can write phi by I is equals to NAB upon C. Can I write it? Phi upon I is equals to NAB upon C. So from here, if you want to increase the sensitivity of your galvanometer, if you want to increase the sensitivity of the galvanometer, what you need to do? Either you can increase the number of turns, either you can increase the area of the coil, the winding coil that you can increase, either you can increase the magnetic field, or you can decrease the torsional constant. Okay, so torsional constant depends on the material. Number of coils you can increase, number of turns that are you are winding, you can increase it by yourself. Okay, area, if you can increase, like keeping a big core you can increase the area. Magnetic field, if you put a strong magnet, more stronger than this, the more the strong the magnet will be, the magnetic field will be much more stronger. Okay, so other things are not in our hand, just we'll mainly talk about number of turns. Okay, so if I increase number of turns from n to twice n, if I increase the number of turns from n to twice n, then the sensitivity will increase from phi by I to twice phi by I, which means on doubling the number of turns, the sensitivity of the galvanometer also increases. On doubling the number of turns, the sensitivity of the galvanometer gets doubled. Okay, now from this galvanometer you can also make voltmeter also, that is conversion to voltmeter and ammeter also, but that will not be talking about in this lecture. We will be just talking about if it is converted to voltmeter, then how can we check the sensitivity of voltmeter also. So for voltmeter sensitivity, I have just rearranged this term. Okay, phi by I NAB upon C. Instead of that, I have written phi by V. If it is, this is the sensitivity for current, then this will be sensitivity for voltage. Okay, so phi by I need to compare it with same. So what I have done, I have divided 1 upon V on both the sides, and I have taken I from over here to over here. Okay, so phi upon V is equals to NAB upon C, I upon V. Okay, now can I write I upon V as 1 upon R? I upon V is equals to 1 upon R. Okay, so from here we get the sensitivity of voltmeter also. Why it is specifically talked about? Because here if you increase the number of turns, the sensitivity will not increase. Okay, why? The reason is, if you increase from n to twice n, what will happen? You think that sensitivity will get doubled, but there is 1 upon R. If you increase the number of turns, what will happen? The length of the wire will also increase. Length of the wire will increase, which means the resistance will also increase. You all know R is directly proportional to L. R is directly proportional to L. Okay, so if R will increase, the sensitivity will decrease, which means if by increasing the number of turns you are increasing the length, and by increasing the length you are increasing the resistance. So n to 2n is compensated by 1 upon R, which means that the amount of sensitivity you wanted to increase is cancelled off by the increase in resistance. So if you increase from n to twice n the number of turns, then also you will have no change in sensitivity. Okay, I hope this topic is very clear to you. Thank you students, have a nice day, keep studying. This was the last topic for this chapter. From next lecture onwards we will be starting with our new chapter. Till then, keep studying, try to make the note of it. Okay, and try to write everything in your own terms. many of you I have seen that they are only writing the things that I have written on the board, but I don't want that. Everyone just try to write it on yourself. Don't just copy blindly from the board. Okay. I hope you all are studying well. Thank you. Have a nice day.